Okay, so for instance, when we were doing those horizontal asymptotes, we had to calculate limits. And L'Hopital's rule has to do with evaluating limits of things. If I were trying to evaluate the limit of natural log of x over x minus 1, all right, and let's say we're doing that when x is approaching 1. We know it's not defined at 1, right? I can't just plug in a 1. But if I'm trying to find this limit, then it gets a little complicated because the natural log of 1 is 0. 1 minus 1 is 0. We don't know what 0 over 0 turns into. So this is what's called an indeterminate form. It's something that we can't just look at and evaluate the limit. So if you have a function divided by a function, it's going to 0 over 0. That's the indeterminate form of type 0 over 0. We've done some previously, but I gave you different tricks for evaluating them, like factoring and reducing, dividing everything by the highest power of x. You know, we've been doing those tricks, but sometimes those things don't help. So we are going to use what's called L'Hopital's rule in that situation. L'Hopital's rule works if you have an indeterminate form, 0 over 0 or infinity over infinity. Okay, and it doesn't matter if it's positive infinity over negative infinity or negative over negative, it doesn't matter there. It's true then that the limit of that division is equal to the limit of the derivatives of the top and bottom. Okay, so this is what it's telling us. It only works if it's 0 over 0 or infinity over infinity. But we can do the derivative of the top, derivative of the bottom, and evaluate our limit. And we should get the same answer. The proof is a little complicated for this, so I'm just going to ask you to trust me, but if you're really intrigued, I would be happy to sit down with you and justify why this is true sometime. But one thing I want to stress, this isn't the quotient rule. It's not the derivative of the whole expression at once. It's the top and bottom separate. So, for example, if I were asking you to evaluate that limit, right now, the natural log of 1 is 0, 1 minus 1 is 0. So it's an indeterminate form, 0 over 0. The only two cases we can do are 0 over 0 or infinity over infinity. Then we can do L'Hopital's rule. I am going to ask that you identify when you do it, so I just usually put LH over my equal sign to say this is where I'm doing L'Hopital's rule. The limit stays the same. What's the derivative of the natural log x? It's 1 over the argument. On the denominator, what's the derivative of x minus 1? 1. So L'Hopital's rule tells me this original limit is equal to this limit. Can I plug my 1 into this? Yeah, we get 1 over 1 over 1, or just 1. Make sure that you are checking that L'Hopital's rule applies. Don't just jump into the problem and start doing it. It has to be 0 over 0 or infinity over infinity first. So if I give you this one, the limit as x approaches infinity of e to the x over x squared. So if I just try to evaluate this, e to the infinity is just going to infinity. Infinity squared is just going to be another really big number. So it's infinity over infinity right now. That tells me we can do L'Hopital's. So I'm going to label the limit as x approaches infinity. So derivative of the top, derivative of e to the x is still e to the x. Derivative of x squared is 2x. All right, if I try plugging in now, what's e to the infinity? What's 2 times infinity? This is still an indeterminate form. So what do you think I could do? We're going to do L'Hopital's again. Now the nice thing is it's not a quotient rule, so we're just doing derivative of top and bottom separately. So derivative of e to the x is still e to the x, but derivative of 2x is 2. So now I have e to the infinity, which is infinity, divided by 2. If you take a really big number and divide it by 2, what are you going to get? Is that okay? All right, so if I look at this one, the natural log of infinity, the log graph just keeps rising, right? So it's going to infinity. The cube root of infinity, infinity. So infinity over infinity. So that tells me we can do L'Hopital's. All right, natural log of x. What's the derivative of natural log x? Okay, the cube root, that's like x to the 1/3. So the derivative of that would be 1/3 x to the negative 2/3. All right. Fairly ugly right now, but we can simplify some. So I would recommend that. Let's clean this up. I have 1 over x. 1/3 x to the negative 2/3 would be 1 over 3x to the 2/3. How do you divide fractions? So then I can subtract the exponents. So 2/3 on the top, 1 on the bottom. So that would be x to the 1/3. So now you have 3 over infinity. What's that turn into?
It's like 0.
A number over infinity always turns into 0. Okay, so L'Hopital's is helping us evaluate limits that we would not otherwise be able to. You know, this one, there was no factoring and reducing I could have done. There was no dividing by the highest power of x with a natural log. So this is another resource that we have. All right. Any questions there? So first we have to try to evaluate it. Tangent of 0, so think about a hand trick, square root of the top over square root of the bottom. So 0 over 2 would be 0. Minus 0 over 0 cubed. So this is 0 over 0, which tells me we can do L'Hopital. All right, what's the derivative of tangent x? Secant squared x. Minus derivative of x. over derivative of x cubed.
Oh, yes. Could you do the top is equal to cosecant, or wait, no, sorry, cosine, wait, no, yeah, cosecant squared x, or what is is it tan squared?
Yeah.
I didn't know which one it was.
Yeah. You can, I don't think it's going to help a whole lot,
Yeah.
but yes, you could, any trig identities that come up, you can definitely use. Okay, what is the secant of 0? So cosine of 0 is 1, so the reciprocal of 1 is 1. So we have 1 squared minus 1, which is still 0 over 0. All right, so then what? Okay, let's try it again. Let's hope it gets better. Okay, you have to be a little bit careful here. When you have this secant squared, that's like saying the secant of x squared. So we have to do the chain rule. So 2 comes down, inside stays the same, times the derivative of the inside. What's the derivative of secant? Secant tangent. It's been a while.
Yes, it
Minus derivative of 1 is just 0 over 6x. Okay. I could reduce my 2 over 6 and just make this 3x on the bottom. All right, if I plug in my 0, secant of 0 is 1, tangent of 0 is 0 over 0. I'm still getting 0 over 0, aren't I? If I do this derivative again, it's going to get pretty ugly because on the top I'm going to have to do product rule and chain rule. So it's not necessarily getting better. We can still use any of our other limit tricks that we have. So what if I separated this? Made it secant squared x over 3 times the tangent of x over x. Do you agree that this is equivalent to the previous line? Our limit rules say we can do the limit of each individually. Right? That was one of our very first limit laws, that if you have things multiplied, you can do each individual limit and multiply the answers. The reason this helps me is because as x is approaching 0, secant is going to 1. So this one turns into 1/3. This is the one that's the problem, right? This is where I'm getting my 0 over 0. So we have 1/3 times this limit. Okay, my limit is still 0 over 0, but what can I do now? L'Hopital's again, but it's so much nicer now because I don't have that secant squared. I evaluated that piece of it. So we have 1/3 times the limit as x approaches 0. Derivative of tangent is secant squared x. Derivative of x is 1, and we finally got it. Because derivative, or secant of 0 is 1, So we have 1/3 times 1, or 1/3. So sometimes you might have to get a little creative. If you are doing L'Hopital's and it just seems to be getting uglier and uglier, then stop and see, can you simplify it in some way? Can we break it apart and evaluate part of it so that we're not getting a terribly ugly expression? I know that one was a little more involved. Any questions on it? Then one more for today. Last one. Limit as x is approaching pi from the left of sine over 1 minus cosine. Sine of pi. You need to think about your unit circle. Pi is right here. That's 0.810. Sine is the y, so that's 0. Over 1 minus, what's the cosine of pi? -1. I just have 0 over 2. Do I need to do L'Hopital's? No, my answer is just 0. Don't assume that every question I'm going to give you will require L'Hopital's. You have to check and make sure it's 0 over 0 or infinity over infinity. If it's not, then you need to evaluate it otherwise. All right. Any questions for me? So I am stopping here.